Imagine an AI, maybe like GPT,
Yeah.
but achieving similar results using just the brain power of a tiny worm. Seriously.
Yeah.
That's kind of the promise behind deep liquid networks, LNNs.
Yeah.
Okay, let's unpack this. Welcome to the deep dive. We sift through the interesting stuff and try to bring you the core ideas.
And what's really fascinating here, I think, is how fundamentally different it is. Standard AI, after training, it's basically frozen.
Right.
Static. Exactly. But LNNs, they have this ability to continuously adjust. They adapt as new information comes in. It's like the network is, well, constantly evolving in real time.
Exactly. And that's what we're diving into today, these deep liquid networks. We've got a great practical guide here. It covers the basics, how to build them, experiment, the whole deal. So our mission for this deep dive is to give you a clear, hopefully engaging look at LNNs. The key designs, how you can actually start building with them, and where to look next if you get hooked. We want you walking away feeling informed and maybe a bit inspired.
And if you think about the bigger picture, the potential is, well, it's pretty huge. We're always pushing for more powerful AI, right? But that usually means bigger models, more energy.
Yeah, the environmental cost too.
Right. LNNs offer this potential path to intelligence that's maybe more efficient, more adaptable, especially where, resources are tight or you need super quick responses.
Okay, so let's get into the nuts and bolts. The guide highlights two main ways LNNs get this liquid behavior. Liquid time constant networks, LTCs, and closed form continuous time models, CFCs. What's the fundamental difference we need to get first?
Well, the absolute core difference is how they handle time. Think about traditional networks, even standard RNNs.
Yeah.
They process information in these discrete steps, like frames in a movie.
Okay, step.
Yeah. LNNs, though, they use differential equations to model their neurons, their behavior.
Ah, okay. Calculus flashbacks.
Yeah, a little bit. But think of those equations as just describing how quickly a neuron state is changing at any moment. Not just at those fixed steps. It lets them handle information continuously.
Okay, continuous versus discrete. Got it. So let's start with the first type, these liquid time constant networks, LTCs. What's the key idea there?
The central thing for LTCs is this idea of a dynamic time constant for each neuron. Imagine, each neuron has its own little internal clock.
Right.
And this clock controls how fast it reacts to new stuff and how long it remembers old stuff. In LTCs, that clock isn't fixed. It actually changes based on the data coming in and what the neuron's already doing.
Whoa, okay, so it's adaptable, not like a regular circuit where everything's fixed speed. These neurons can actually speed up or slow down their own reactions.
Precisely. That's the liquid part. If the input's changing really fast, the neurons might shorten their memory, focus on what's happening right now. If things are slower, more stable, they can lengthen that memory, capture those longer trends.
That makes sense.
And this on-the-fly adjustment is the big advantage over traditional RNNs, which have a fixed way of dealing with time. Mathematically, it's all governed by those ordinary differential equations, ODEs, telling us how the neuron state evolves based on, how forgetful it is and the signals it gets.
Okay, dynamic time constant, ODEs.
Huh?
Sounds powerful.
Yeah.
But the guide mentions computation involves numerical ODE solvers. What does that mean practically? Is it slow?
Right. This is where it gets a bit more technical. To actually simulate that continuous change described by the ODEs on a computer, you need these numerical solvers. Think of them as taking tiny, tiny little snapshots in time to approximate the continuous flow.
Okay.
Now, this gives you a really accurate picture of the dynamics, but it can be computationally heavy. You might need lots of these tiny steps for each bit of input. So yeah, it can slow things down, especially during training.
Got it. Brilliant idea, maybe a bit demanding computationally, which I guess leads us straight to the closed-form continuous time models, the CFCs. They're meant to fix that bottleneck.
Yeah, exactly. That was the goal. The researchers behind CFCs wanted the benefits of LNNs, that continuous dynamic, but without the heavy cost of the ODE solvers. And the speed-ups they found are potentially massive. We're talking orders of magnitude faster.
Well, yeah, magnitude. Wow. Okay.
Yeah, with supposedly minimal loss in accuracy. The core idea is finding an approximate analytical solution, a closed-form solution to the math governing the state change. Meaning you can basically calculate the new state directly in one go. You don't need all those iterative tiny steps from the whole.
Okay, that sounds like a game changer for speed. How much faster we're talking?
Yeah, it cites 1 to 5 orders of magnitude faster compared to LTCs with the numerical solvers.
That's huge.
It really is. And apparently this comes with Less than a couple of percentage points drop in accuracy on some tasks, which is pretty remarkable. Now, to make sure this approximation is stable, they usually build in things like a bounded gating function and a learnable scaling factor. Little tweaks for stability.
And the benefits go beyond just speed, right? Something about memory usage and reaction time.
That's right. Because it's basically one calculation per step, CFCs don't need to keep storing large hidden states at every single time point, unlike some other recurrent models. So memory usage stays pretty much constant, even for really long sequences.
Okay, efficient.
Very. And because it's that single calculation, the latency, the time to get a response is also really low. That makes them super attractive for, real-time stuff, edge devices where you need quick reactions and don't have tons of power.
So both LTCs and CFCs, they're liquid because they're constantly adapting internally to the incoming data stream. Handles dynamic stuff way better than static networks. Okay, I'm really starting to see the power here. So how do we actually get started? What setup do we need?
Right. The guide really focuses on using either PyTorch or TensorFlow. They're the big players in deep learning frameworks.
The usual suspects.
Yeah. PyTorch is often loved for its flexibility, easy debugging, especially in research because of its dynamic graph build.
Yeah.
TensorFlow, on the other hand, is really strong for deploying models out into the real-world production environments. And the good news is the NCPs library we'll talk about supports both.
Okay. And step one, always step one. Virtual environment.
Absolutely crucial. Cannot stress that enough. Use Vem, use Conda, whatever you prefer, but isolate your project's dependencies. It just saves so many headaches down the line. The guide gives the basic commands, python-mv mine, mynv, activate it. Standard stuff, but essential for ML work.
Right, got the environment. Now installing PyTorch or TensorFlow.
For PyTorch, the best way is definitely their official website, pytorch.org. They have this neat little configurator. You tell it your OS Python version, whether you want CPU or GPU with CUDA.
Oh, yeah, I've used that. It spits out the exact pip command.
Exactly. Super helpful. The guide shows an example, reminds you to tweak it for your CUDA version if you're using a GPU, and run the little verification script afterwards, just to be sure. For TensorFlow, it's usually a simple pip install TensorFlow. Just double-check their required Python version. And again, verify the install.
Okay, framework installed now. The magic ingredient.
Yep.
NCPs.
Yep. NCPs stands for Neural Circuit Policies. This is the key library for actually building the LTC and CFC models. Developed by the main researchers in this area, installation, simple pip install NCPs. That one command gets you the tools for both PyTorch and TensorFlow.
Nice and easy. Now, GPUs. Everyone loves speed.
Yeah.
How does GPU acceleration work with these LNNs? Is it worth it?
Well, LNNs are designed for efficiency, but yeah, GPUs can still give you a significant speed boost, especially for more complex models or really long data sequences. For PyTorch, you need the NVIDIA CUDA toolkit and the Cudahy library installed, and they have to be compatible with your driver and the PyTorch version you installed. You pick the right CUDA version during the PyTorch install. TensorFlow is similar. Compatible NVIDIA drivers, CUE toolkit code, DNN SDK. One thing the guide notes. For Windows users with TensorFlow 2.10 or newer, the recommended route for GPU support is often using WSL2, the Windows subsystem for Linux.
Right, WSL2. Good tip.
Yeah.
So installing NCPs is easy, but getting the whole environment, the framework, CUDA, cuDNN, all playing nicely together, that's the potential first hurdle.
That's absolutely it. It's often the first challenge. Take the time, follow the official PyTorch TensorFlow guides carefully. Making sure those versions align saves a lot of frustration later. Even though NCPs hides a lot of the complexity, you still need that basic framework understanding.
Okay, environment sorted. We're ready to build some liquid networks. Seri NCPs, the library from Lechner, Hassani, and the team. Inspired by the C. elegans worm, how do we actually define an LTC or CSC layer with it?
It's actually pretty straightforward in NCPs. In PyTorch, you'd import LTC or CFC from ncps.torch. Then you just create an instance, telling it things like your input size and the number of units or neurons you want.
Okay, like defining any other layer.
Pretty much. The guide shows simple examples for fully connected LTC and CFC layers in PyTorch, and it's very similar in TensorFlow using ncps.tf. You get Keras layers, LTC, and CFC that you can slot into a Keras model. Key parameters like number of units, whether you want the whole sequence output or just the last step, return sequences, they're generally consistent. They also offer N-cell versions for more fine-grained step-by-step control, but usually you'll use the full RNN-style layers for sequence data.
Now, the guide mentions wirings quite a bit. Sounds different from just standard, fully connected layers. What's the deal with wirings in NCPs?
Ah, yes, wirings. This is a really cool and important part of NCPs, especially for the neural circuit policies idea. Wirings define how the neurons are connected. Instead of every neuron connecting to every other neuron, wirings let you create sparser, more structured connection patterns.
Like in a real brain.
Exactly.
Yeah.
Often inspired by biological neural networks. This sparsity is a big reason why these models can be so efficient.
And NCPs helps you create these wirings. There's something called AutoNCP.
Yeah, AutoNCP is super handy. It's a class in ncps.wirings. You basically just tell it the total number of neurons you want and how many should be output or motor neurons. It then automatically generates a biologically plausible, sparse wiring structure for you.
Right.
The guide shows a PyTorch example. Create an AutoNCP object, then pass that object to the units parameter when you define your CFC or LTC layer. In TensorFlow, you often pass the wiring config as the first argument. It's the recommended way to start if you want sparse networks without designing them manually.
So AutoNCP for automatic sparse wiring. And if I just give a number for units.
Then you get the standard fully connected setup. NCPS uses fully connected wiring implicitly then. If you want really explicit control, there's also ncps.wirings.ncp, where you can define sensory neurons, interneurons, motor neurons, and exactly how they connect. More advanced, but gives you total control.
Okay, layers, wirings, any other key settings we should know about when using these NCPs layers?
Yeah, a couple of important ones. First, mixed memory. This is available for both LTC and CFC layers. If you set mixed memory true, it basically bolts an LSTM-style memory cell onto your LNN neuron.
Ah, like a hybrid.
Exactly. LNNs are great with their continuous dynamics for time dependencies, but sometimes that explicit long-term memory date from LSTMs is really helpful, especially for super long sequences. It's like getting the best of both worlds.
Interesting. What about settings just for CFCs?
For CFCs, you've got parameters like mode, backbone units, and backbone layers. The mode affects how closely the CFC approximation tries to mimic the underlying LTC dynamics. The backbone is a small internal neural network, an MLP, that helps compute the CFC state updates.
Okay.
So backbone units controls how many neurons are in the layers of that internal MLP, and backbone layers controls how many layers it has. You can tweak these to trade off a bit of speed for potentially more complex internal calculations. The guide has a nice table summarizing these key parameters for PyTorch layers, and notes TensorFlow is generally similar.
All right, we've got the concepts, the setup, defining layers, time to actually build something. The guide suggests time series forecasting as a good first project. Makes sense. What's the goal?
Yeah, it's a natural fit. The basic goal is simple. Look at past data points in a sequence, predict the next one, like predicting tomorrow's temperature based on the last few days. LNNs are built for finding those temporal patterns.
And for a first try, the guide says use synthetic data, like a sine wave. Why start there?
It just makes life easier initially. With the sine wave, you know the underlying pattern perfectly. You can generate clean data easily, no weird noise or missing values like in real-world data.
Right, so you can focus on whether the LNN is actually learning the time aspect.
Exactly. It simplifies debugging. The guide gives the Python code using NumPy to generate a sine wave, maybe add a bit of noise, and then crucially, chop it up into overlapping sequences suitable for an RNN input. It explains sequence length, how many past steps the model sees to make the next prediction.
Okay, synthetic data prepped. Now, building the model in PyTorch with NCPs for this forecasting job.
So the guide walks through making a PyTorch NN module. Let's call it time series CFC. Inside, you define your CFC layer. It suggests using AutoNCP for the wiring, which is a good default.
Right, the sparse wiring.
Yeah. You need to tell the CFC layer the input size, which is 1 for our single sine wave value, and pass in the AutoNCP wiring objects you created. The output size of the CFC layer is determined by the motor neurons you set in AutoNCP. Then, typically, you add a standard linear layer and nlinear to map that CFC output to your final prediction, which is also size 1 in this case.
Gotta match the dimensions there.
Critically important. The guide stresses matching the CFC output features to the linear layer's input features. It also mentions using return sequences. True if you want the output at every step, but for this kind of forecasting, you usually just take the output from the last time step of the sequence to predict the next single value. Then you set up your loss function. Mean squared error is standard for regression like this and an optimizer, like Adam.
Okay, model defined, loss, optimizer ready. Training time.
Yep, standard PyTorch loop next. First, convert your NumPy data arrays to PyTorch tensors. Then wrap them in a tensor dataset and a data loader. The data loader handles batching and shuffling for you, which helps training.
Wait.
The loop runs for a number of epochs. Inside the epoch loop, you loop through the batches from the data loader. For each batch, zero the gradients, Put the model in train mode, feed the input sequence forward through the model, get the prediction, calculate the loss compared to the actual target value, call loss.backward to compute gradients, and then optimizer.step to update the model weights.
The standard dance.
The standard dance, exactly. The guide adds code to print the average loss per epoch, maybe store it so you can plot the learning curve later.
And after training, we want to see how well it learned the sine wave.
Right.
Evaluation, visualization.
Absolutely. You switch the model to evaluation mode, model.eval, and use torch.newgrad to turn off gradient calculations, saves computation. Then you feed your test data, or even the training data for this simple case, through the model to get predictions. Collect the predictions and the actual target values. The guide shows using matplotlib to plot the predicted sine wave right on top of the actual one. That visual check is super valuable to see if it captured the pattern.
Nice.
And it briefly mentions, the equivalent steps in TensorFlow Keras. Use ncps.tf layers in keras.model, model.combat, model.fit, model.predict. And it points again to the NTP's Colab notebooks, which are great interactive examples for both frameworks.
Okay, first LN built and trained. That sine wave is looking good. Now, if we want to go deeper, explore more advanced stuff, what are the key resources? Where should we look?
The guide points to a few absolutely crucial GitHub repositories, mostly from the key researchers Riman Hassani, Matthias Lechner, MIT CSAIL folks. There's Raman Liquid Time Constant Networks, that's the original LTC stuff, TensorFlow 1.x based, but has great context and example data sets.
Okay, good for history and data.
Yeah. Then Raman HECFC has TensorFlow 2.x and PyTorch code specifically for CFCs with some practical examples. But the main one, the one you'll probably use most for current development, is Molect26 LNCPs.
That's the main library we've been talking
That's
about.
exactly. PyTorch and Keras implementations of NCPs, LTCs, CFCs, it's robust, well-documented, tons of examples, tutorials, those Colab notebooks, it's the go-to. There's also Raman Liquid S4, which is really interesting, exploring combining LNN dynamics with state space models for super long-range stuff.
Cutting edge.
Definitely. The guide strongly advises focusing on these core repos from the main researchers. A general search for liquid networks might pull up unrelated things, so stick to these primary sources.
Good advice. It sounds like research is moving fast, too. Specialized architectures beyond just LTC and CFC.
Oh, yeah. The guide mentions Liquidforia latent dynamics networks, LFLD nets from Stanford. These are designed for complex space-time modeling, like simulating physical systems governed by partial differential equations. They actually use sparse LNNs from NCPs combined with other techniques like Fourier embeddings.
Wow, okay.
The existence of things like LFLD nets and Liquid S4 just shows this is a really active field. People are constantly extending and adapting LNNs for tougher problems.
And what about the wider community? Any other interesting takes or implementations popping up?
There are others out there. The guide mentions a few, like Key-Gomez LiquidNet, Ipsita Liquid Networks, both PyTorch, Siraj Deep Liquid Neural Network, LN, Jupyter. These might explore multi-layer LNNs, mixing in attention mechanisms, stuff like that. They offer different perspectives, maybe some newer ideas. But again, the recommendation is usually start with NCPs for the solid foundation.
Right. Stick to the well-trodden path first.
It's often wisest. And you see this trend, like with Liquid S4, of hybridizing LNNs with other successful ideas. Combining strengths seems to be a key direction. The guide includes a really handy table summarizing these key repos and libraries, maintainers, frameworks, models, links. Super useful reference.
Okay, we know the tools, the resources. What kinds of projects beyond the sine wave are good fits for LNNs? And what data sets work well?
Well, their core strength is time series, right? So anything involving sequences over time is a good candidate. The guide suggests things like financial data analysis, sensor data from IoT devices, environmental monitoring. It points back to those traffic.py and ozone.py examples. Human activity recognition from sensors, har.py example, and especially physiological data, ECG, vital signs.
The medical field.
Yeah, LNNs seem particularly promising there, especially because they can handle irregularly sampled data, which is common with patient monitoring. The PhysioNet Challenge 2012 dataset is mentioned, and the newer PhysioMAOD benchmark specifically targets this irregular sampling challenge.
Interesting niche.
Definitely. Beyond time series, there's potential in control systems and robotics, drone control, autonomous driving maybe. And because they're efficient, edge AI applications are a big target intelligence on small devices.
Where do we find data for these?
Again, the datasets bundled with NCPs and the original LTC repo are great starting points. Standard benchmarks like PhysioNet, Mujoko physics simulations, USHCN climate data. For irregular time series, PhysioMAOD is key. And then the usual suspects. Kaggle, UCI Machine Learning Repository, Papers with Code has dataset links too. The guide has another table matching project ideas to LNN suitability, datasets, concepts to explore, and potential challenges. Really helpful for brainstorming.
Okay, project ideas brewing. Let's talk practicalities. Getting these models to train well, tuning them, debugging. Any tips?
Tuning can be a bit involved. There are quite a few knobs to turn, especially with the NSPECE layer parameters, wiring choices, ODA folds for LTC, the mode and backbone settings for CFC, mixed memory, plus the usual suspects like learning rate, batch size.
Yeah, lots of hyperparameters.
It's a complex space. The guide actually suggests using automated hyperparameter optimization tools like Raytune or Optuna to search more systematically. Otherwise, it can be a lot of trial and error.
What about common problems? What goes wrong?
Well, you can still run into vanishing or exploding gradients, like in other RNNs. Gradient clipping can help there. For LTC specifically, the ODE solver performance versus accuracy trade-off with ODA folds is something to watch. CFCs mostly avoid that.
Right.
Overfitting is always a risk, especially if you make the wiring or model too complex too quickly. Start simple. And while LNNs adapt, if your data fundamentally changes over time concept drift, you might still need occasional retraining. Stability is generally a design goal, but something to keep an eye on.
How about debugging? Are they black boxes?
Smaller NCP models can actually offer some interpretability, which is nice. You can sometimes visualize neuron activations or attention flows. But a really practical tip from the guide is check the GitHub issues section for the NCP's repository.
See what problems other people hit.
Exactly. It's a live database of common errors, compatibility issues, maybe weird behavior with specific TensorFlow versions, scaling advice, problems with AutoNCP. You can find solutions and workarounds there. Beyond that, standard debugging applies. Start simple, check your data shapes meticulously, monitor the loss. Is it man exploding, vanishing? Fiddle with the learning ring. Check weight initialization.
And best practices overall.
The guide sums it up nicely. Start with CFCs, usually, for speed. Use AutoNCP for sparse wiring, unless you have a reason not to. Normalize your input data, always important. Use regularization like dropout. Consider learning rate scheduling, like reducing it if the validation loss plateaus. And definitely use early stopping based on a validation set to prevent overfitting and save time.
Okay, so it feels like LNNs are really buzzing. Dynamic, developing fast. What's the future look like? Where's the research heading, and how can we keep learning?
The future looks really active. You've got ongoing work on hybrids like Liquid S4, combining LNN ideas with other powerful architectures, development of more specialized versions like LFLD nets for specific complex problems. A big push is always on scalability and efficiency, making them even better for edge devices and maybe even larger scale tasks.
And the theory behind them.
That too. Researchers are digging deeper into understanding their fundamental properties. Exactly how much can they represent expressive power? How well do they generalize to unseen data? What guarantees stability? Can they perform causal reasoning? Lots of foundational questions still being explored. And broadening applications beyond time series and control, looking at NLP, vision, more complex robotics.
Who are the key people to follow?
Ramin Hassani at MIT CSAIL and Liquid AI. Matthias Lechner, now at IST Austria, formerly MIT, they are central figures. Following their work, their GitHub profiles is key. Daniela Rus at MIT CSAIL is also a major figure in related robotics and AI areas.
And for staying updated.
Actively watch those key GitHub repos, especially in NCPECE. Read the code, examples, discussions, and issues, and pull requests. Keep an eye on archives, preprints, and papers at major ML conferences like NeurIPS, ICML, ICLR. Look for technical blogs and articles summarizing progress, and keep an eye on Liquid AI, the company, as they might drive commercialization and future developments. Basically, it's a field moving quickly. You got to stay engaged with the research community to keep up.
Right. So wrapping up, deep liquid networks, they're this really fascinating alternative, potentially much more efficient way to do deep learning. All about continuous time dynamics, adapting on the fly. We've looked at the core ideas of LTCs and CFCs and how NCPs gives you the tools to start building them. Their strengths really shine in time series, control, edge AI, especially with messy, dynamic, or irregularly sampled data.
Definitely.
So if this sparked your interest, seriously, check out the GitHub repos, especially Malek 26 LNCPs. Try that sine wave forecasting project, or maybe adapt it to some simple real-world data. Dive into the papers if you're feeling adventurous.
And maybe, as a final thought for you to chew on, given that these LNNs are inspired by biological brains, however simply, and they promise more adaptable, maybe more robust AI, what kind of impact do you think this bio-inspired approach might ultimately have on where AI goes next? Could it lead to something fundamentally different down the road? Definitely something to think about.